So I wanted to talk a little bit about vision and language and give you a little bit of a few commentary around these two technologies that we have been hearing for a while in these previous presentations. So first, I wanted to give you a sense of how fast things have changed. So imagine that you are a student in 2005, like I was at some point, and you want to build a new system, and you had to know a lot of things. There were a lot of different technologies and different pieces of math and algorithms that you need to be quite proficient in order to be able to build, let's say, a computer vision system. And if you missed any of these things, there were a handful of papers that you were not able to understand. It was really necessary to know, like, have a very broad perspective on a lot of different technologies. The picture has dramatically changed in the last few years. Now, it's all about deep learning. You still need to know a lot of things, and it's still very useful to know all of this, but for very different reasons. So, you're a student, you have learned all of those things, and then now you're ready to use your favorite computer vision system, you train it, you want to run it in some image, so you have this image here, you run the system to recognize all the objects present, and this is the output. And then you had to publish a paper with this and say, this is better than what it was on the past. And the reviewers will look at it and they will say, yeah, it's true, it's better. It was difficult to do things. But still, people managed to get their papers in, surprisingly. But it was hard. It was hard because you had to know a lot of things and nothing was really working. And part of the things that you had to do is that you had to label a lot of images and you had to create data sets. So just to give you a sense of how fast the field of computer vision was evolving at that time, this is a few indications of what things, how things evolve over time, starting in the 90s, 95. So part of the progress was about the benchmarks, the data sets that were used in order to train systems. And, one important object class that people care about was cars, detecting cars in images. So this is what a car was in 95. It was a toy car on a black background, because if you had a background that was different from black, nothing worked, as soon as it was complicated. And then you had different viewpoints of this object. There were a few more things, but basically this is what we had. And it took almost 6 years to start getting people really losing, not being afraid of working with real images. I'm making a caricature here, but it kind of gives you the idea of what was happening. So this is another data set that contained cars on real images, but only side views. This is the view that was used, and there were no frontal views or anything else, just side views. And it still was really hard to make systems work with this type of images. Then, a year later, we were able to look at the back of cars. And then in 2007, more than a decade later, a benchmark like the Pascal dataset appeared, which was a lot more challenging, images captured by people that were not in the field, with cars in all possible poses, all different kinds of styles. And it was just very hard to make anything work. So things were evolving quite slowly. And you had to, in order to train the system, you needed a lot of images. They had to be hand-labeled by humans. And it required a lot of work just to get started. And in particular, in order to annotate these images, so you need to hire people. In my case, we hired my mother. She's been labeling images since 2007. She's still labeling images, but for other reasons. So this is just a year ago. And she's been labeling images for a long time. She's labeled more than 1 million objects. So it's just probably the most experienced image labeler that there is out there. So the period between 2000 and 2015, I will say that was the benchmark golden age, where we knew exactly what we wanted to do. We wanted to detect objects in images, or maybe we wanted to do language translation. We knew exactly the things that we wanted to do, and we knew exactly how to evaluate them. So there were benchmarks like the Pascal dataset in computer vision that was used to measure the performance of a computer vision system in recognizing a set of possible object classes. Then there were things like ImageNet that will give you the potential to measure the performance of a system capable of classifying an image according to 1,000 possible labels. So we knew where we wanted to go, and we knew how to measure things. And people will then have these plots showing performances and comparisons between different algorithms, and it was great. And it created a lot of excitement, and it actually motivated a lot of the progress that gave rise to the deep learning era. But I will say this age is over now. And the reason is because now we have systems that can do a lot of things. In fact, we don't know anymore what we want to do with them because they can do things we were not expecting, and we don't know how to measure performances. So in the past, we had benchmarks that were way ahead of the models, and now I will say that our models are ahead of the benchmarks. We don't really have good benchmarks to measure what these models are doing. And you can actually ask these models to do quite sophisticated things like ChatGPT. You can put them like a math problem that a college student could solve, very young student could solve. And the system will just output something, and it will do it in really nice English, explaining the reasoning of how you need to compute different quantities in order to get to the final math result. The only thing that it happens to be wrong, but that's a different question. But it's just capable of doing something very nice. And there are many, many things that you can ask for. And evaluating all these things is just tricky, and it's not clear how to do it. And now we have multimodal AI, where things are even more complicated in terms of evaluation, because now you can have systems that you can input text and images. And this is a test I did with GPT Vision, where I asked what happened in this image. And it goes through some neural network, and then it outputs some text that describes quite nicely what happened here. And I was quite surprised, because this is kind of a strange situation. And I was expecting that maybe it could have said, well, there's some people that want to swim on the swimming pool, and it will have been fine. No, it actually looked at the car, it noticed that this is the thing to talk about, and describe the situation around this. It's just kind of impressive. How do you know how well the system is performing? It's just very difficult to evaluate, given the amount of things it can do. And there is a lot of research now that tries to answer the question of how to evaluate these models. But that's not what I'm going to talk about. So in the last decade, there has been a lot of progress. From 2012, where the first neural networks that were successful at the ImageNet Challenge were proposed, until now, just a bit over a decade later, there has been so much progress, from very simple systems to systems that now can perform complicated queries in a multimodal setting. If you compare that with what was happening in the first decade, the first part of the century, it's just impressive the speed at which things are changing now. It's basically the same amount of time that we go from simple neural networks to agents that took from going to toy cars to real images of cars in any kind of pose. So this is quite interesting. There's been a lot of progress in generative AI in general. And if you think of 2014, when the first generative AI models were proposed for images using neural networks. Generative AI has a very long history and exists way before that. But using neural networks, around 2014 where the first models were introduced. And this was one of the examples shown in the original paper that introduced adversarial neural networks, showing an image that is generated by a neural network. And to the field at that time, it just looked really cool. It's just very surprising that it can do this. Of course, nowadays, it just feels like, what is this? It's hard to believe that anybody will feel excited by this and decided that they want to spend the next 5 years working on this, because what can go wrong with it? If you are starting your PhD, what can go wrong at the end of your PhD? But just the field moved so fast that just 4 years later, these are the images that were generated, basically by the same idea, still adversarial neural networks, where the models, the neural networks, were just larger. They had more computational resources. They were also this understanding at that point that having very large neural networks was really something that made the systems work better. And this is the type of images that were generated. Still not great, but it it was just spectacular that it was capable of generating something that looks like a horse and maybe something like a person on top of it. It's not a great person, but it's OK. And not just even a decade later, these systems are capable of generating images like this. So the amount of progress has been just impressive. And these systems, the systems that exist nowadays, are based on diffusion models, which I'll just give you a hint of how they work. They are relatively based on a simple idea. Getting them to work is always complicated, as you know, if you have tried to make any of these systems work. There are a lot of engineering that goes into them, but the key idea is relatively simple to understand. So let's say that you have a picture, like this one here. This is a classical problem that people have been working for a long time. You send this picture through a channel, let's say the radio waves, and then it arrives to a TV set. What happens is that as it goes through the radio waves, noise will get added to this image. So there will be some noise, and what you will see on the receiver is a noisy version of this picture. And one of the goals of the TV set is to remove that noise and to show you the original clean image. Well, it turns out that neural networks are really good at solving this problem, going from a noisy picture to a clean image. And you can train a neural network to solve this task in a supervised way, because you can take clean images, artificially add noise, and then teach the network to go in reverse. What is really amazing is that these neural networks are so good at removing noise that you can start just with noise, tell it that there is some picture hidden behind the noise, and the neural network will give you actually a picture. Generally, this will require multiple iterations, but it actually, more or less, the main idea is this one. It will just work. And generally, these models are multimodal, and there is a hint given with text saying what is the picture that is hidden behind the noise. And the neural network in this moment is just trying to remove noise and extract the picture that is hidden behind it. So this is what is known as a diffusion model. It's just when this process is iterative. And these models are actually quite amazing in what they learn. So they learn in this setting that is quite unstructured. You have images and captions that allow you to train the systems to the noise images. But otherwise, there is not much more than that. The training data doesn't need to tell the system what is each object on the picture. It's just a generic caption that goes with the image. And then now you have systems like DALL-E that you can input a sentence like a cup of coffee, and it will output this image, or say a cat, and it outputs an image of a cat. And if you ask for a cup of cat, which requires composing these two concepts, it outputs something like this, which is kind of amazing that it's capable of doing something that looks so strange. There is always the question about what is that it has learned from the web and what is actually being made up by the system. And actually, if you go to Google and you query a cup of cat, you'll find that there is a lot of pictures of people that put cats inside coffee cups. I don't know why, and they take pictures of it. Anyway, so it's seen something like that already. But there are a lot of problems also. For instance, if you ask DALL-E to render an image of a blue cube on top of a red cube beside a smaller yellow sphere, this was in 2022, this is what it renders, which is all wrong. There are the elements. Some of the elements are there. They just have the wrong shapes and the wrong colors, and the spatial ordering is all wrong. So yesterday, well, just a few days ago, I just did the same thing with GPT Vision to see what happened, and this is what it output. So it's still wrong. It's, I will say, a step backwards, maybe, because now it's mixing the objects. But anyway, this is the interpretation it had of that particular query. Another really important aspect of generative AI that I think is the trend that is going to be happening, well, is actually happening now, and it will move forward even more in the future, is video generation. So everything that is happening is mostly about images. And in fact, even GPT Vision is mostly about language and static images. You can put a few images, but it's all about the static. It's everything static. Working with dynamics is what remains as the next frontier. And so there's been a number of attempts in making models that deal with video. So here is a a generative model that generates video sequences. This was introduced by our group in 2016. In this case, it's rendering an image of two people walking on the sand. It's just hard to tell that there is people there. You just see two blobs moving. It's OK. You believe me, they are people. Maybe there are some waves on the background. Nothing very exciting. But in 2022, just a year ago, this was another system introduced by Meta, rendering videos from captions. And this one is really impressive. But it took longer than with images. And these are just very short video sequences that they generate. And just a few months ago, this other system, also introduced by Meta, was produced. There are others introduced by other big labs, like NVIDIA and so on. This one here, it generates just these very impressive sequences just from a caption. So this is an area that still will evolve quite a lot. There is a lot of work that needs to be done. This is far from solved. The videos are not great necessarily. There are a lot of failures. But there is a lot of effort now into making these models to be temporally consistent and also three-dimensional, so that you can actually change the camera viewpoint. But the thing that is happening right now, and it's been already going on for a few months, is everything that has to do with multimodal agents that use AI. So in this case, you will have a human that will send multimodal data to an agent. And as we have been seeing in the previous presentations, now the agent can deal with all that information. And it also has access to tools that it can use in order to address some of the questions that the user has. And these agents can also perform planning. So now you can have systems that interact in more complex ways, where you have an agent and a human. The human might give some patient report, let's say, and it's asking for a diagnosis. And the agent will say, well, there are three possibilities. But instead of giving this answer to the human, it might give this answer to another agent. And the agent might have a different opinion and disagree with this and recommend requesting for additional information. And then the first agent, that is the one in contact with the human, will ask for additional information. The human might then give you a picture. And the system might decide now to request information from the database of electronic health records. And then based on all that information, make a recommendation that the human then will use to make the final diagnosis and provide an answer. So these type of interactions that are more complex, that will involve multimodal data, but also multiple agents with different competencies, is going to be the landscape in which things will start to work. So just to show you an example of why it's important to have multiple agents working together, here is the example that I showed before, where there is this simple math problem that is posed to an agent, and the agent gave like a perfect written answer. It just happened to be numerically wrong. What happens if you ask this to another agent? So you just launch again another window with ChatGPT, and you ask the same question. They never answer the same thing. There is always some randomness to their answers. Well, in the second instance, it happened to be right. So what can you do now? OK, of course, as a human, you don't need to know which one of the two is right. You just want them to be right. So one thing that you can do is you can give to the first agent the response of the second agent and say, here there is another agent that says something different. Here it is. And then you ask, what do you think now? So this is the response of the first agent after seeing the response of the second. And it say, oh, after reviewing the solution provided by the other agents, I agree with the second agent who found that the result is, and it revised its result. You can do the same thing with the second agent, and you can pass the wrong answer of the first agent. And it says, well, after reviewing that, I also agree, and it still gives the right answer. So they both converge to the right answer. And so this was part of a paper that has been done by two students here, Jinlun and Xuangli. And here's another example, like if you ask, what is the result of this complex math problem? Well, not very complex, but complex for ChatGPT. You ask to two different instances, and both get it wrong. Both of them got it wrong. But now, once you cross them, they see that, OK, there is no agreement, so I'm going to recompute things. And in the second round, one of them got it right, but the other one still got it wrong. So you just keep repeating this process, and eventually both of them got it right. And what seems to be interesting is that across a number of different benchmarks that measure performances on arithmetics, on recovering factual data from bibliographies, and so on, all the performances got improved once you have these agents debating by looking at the answers of the others. And it works better than if you just do majority voting between the different answers. Also, as this plot here shows the performance as we increase the number of agents, it doesn't seem to saturate. At least we didn't find it, given our budget. So we couldn't run very large experiments. But the more agents we had, giving different answers and then debating between them, the better the results were. Another thing that is also quite interesting is that multimodality is always there, even when you don't want to. So in the case of language models, the first language models, they were trained only with language. And as it was already mentioned in the Sparks paper in 2023, just at the beginning of the year, even when you train a model only with language, with text on the web, that text also contains code. And you can think of code as a different modality, where you have now English or different languages, but you also have code that actually connects language with actions. So there are a number of really interesting experiments that were shown where you can actually ask a language model to return code that draws a picture. And when you run that code, an image appears. So it is multimodal in some sense, because now you have these different modalities. One of them is connecting to something that looks more into the physical world. So we were trying to explore how well these models actually have an understanding of the visual world, despite that they've never seen images before. The only thing that they've seen is code that makes reference to pictures. And so here is an example where we ask the language model to draw a swivel chair. And it returns some code. And if you render it, it gives you something, well, it's not too bad. It has some other elements. But I think there is something about these language models that make them a little bit lazy when they give you the first answer. So if you just say, well, just do it better. So now you just, can you make it better? And repeat the process. The next time it does something like this, which still doesn't look very good, but it looks definitively better. You can repeat this process again, and now, this is not too bad. It got a few more elements. Now it got the wheels, and you can just repeat this process, and eventually it's just doing things that kind of look fine. It's not great, but they look pretty nice. They have all the elements. You can actually recognize what the object is. And even more interesting is that you can actually have a human draw a picture, and then you draw the picture with very simple geometric figures, so that it's very easy to translate into code. And now you take that code, and you pass it to the model, to the language model, and you ask, what is this? Can you recognize it? So what will it output? So here there are a few drawings that are made by humans on Mechanical Turk. And we asked the model, what is this? And this is what the model was answering, which I think that the ones on the top are really nice drawings. The one on the bottom, I personally am not sure what they are. But these are the predictions from the model. And these are the ground truth data. So the bottom three, it got it wrong. The top three, it got it right. I think that in the bottom three, I think I will have gotten them wrong too. So I think that we need to look really well at human performance in this task. But clearly, this model has the capability of understanding code and understanding what it means in the visual domain. To some degree, not very much. So finally, one of the challenges is that these models, they are learning from a lot of data, but we are kind of running out of data. So a big trend that there is now in the community is on generating synthetic data in order to train these models. And Marcia later will tell us why synthetic data is really bad. But in the meantime, I think that synthetic data is one of the things that a lot of these systems are using in order to train and go above the performances that just the data that you have available allows you to have. So I think that right now we are living in this time where we are relying on these systems to learn from a lot of data and use massive amount of compute in order to build systems that are huge and that learn from all of that data. And I think that we are living in an age where in perception, which is the field I work in, is mostly about computation. Okay? You don't care anymore about how you capture the images. You just have images, and it's about throwing a big machine on top of it in order to understand those pictures. But there was a computer vision, well, a vision person. I wouldn't say computer vision because there was no computer vision at the time, but it was mostly like a cognitive psychologist, scientist that had the dream of direct perception. And what this consisted in was the fact that he believed that all of the information that arrives through your senses to you contains so much information that is enough to make inferences about what is going on in the real world without you needing to have very expensive computational machinery behind it, which is very different from what we have nowadays. And in fact, if you think of a robot, robots like the ones that Dylan was talking about, or real robots that you can see around, this is a picture of the Atlas robot that was used in the DARPA challenge by MIT. They are loaded with sensors. They have LiDARs, stereo cameras, pose, velocity sensors, and pressure sensors in the feet. But if you look at the scientists behind, looking at the robot, trying to make sure that nothing bad happens to it, that is a real system loaded with sensors. It has millions of photoreceptors, which probably are matched by the cameras of the robot, but it has touch sensors, taste sensors, odor sensors. There is nothing like that in the robot. In fact, I will say that the challenge is that now we are in this age of computation, and sensing has become kind of small, but I feel like one of the things that will happen in the near future, and then it will get reversed again, is that sensing will have a very important role to play. And the reason is because we humans, we are multimodal systems. We learn from a lot of types of data, and this is really important for us. And if you think of the story of sensors, cameras and microphones, they have a very long history. However, there is this sensory modality that is very important to us, which are tactile sensors. We have a skin that senses the world around us in our entire body. But the story of tactile sensing is very, very short. There are very few sensors out there that are commercial grade that have high performance. In fact, there is almost nothing. And when you think of sensors, tactile sensors in the world, generally are grippers with a few sensors, maybe digital fingertips, just everything very, very small. One remarkable example of progress in this area of developing tactile sensing is GelSight, created by Ted Adelson here at MIT, where he introduced a very interesting technology to capture high-resolution tactile images, mostly limited to creating very nice pictures that will correspond to something like your fingertips. But something that is wider is just very hard to accomplish. So in collaboration with Wojtek Matusik here at MIT, in a project that was led by Alisa Luo, a graduate student here at ECS, we work on developing tactile textiles that will allow you to build a skin that will cover the full body and being able to sense the full body, what is happening around. So here is an example of a glove that has this type of tactile sensing capabilities and is capable of then capturing images of the pressure of as the hand interacts with objects in the world. So you can use that in order then to, for instance, predict how objects will move when you are manipulating them and so on. But one thing that I found it very interesting is that something really interesting happens when you put tactile sensing everywhere, but in particular in the feet. You can actually create pretty high-resolution images of the pressure that your feet produces on the ground, and that signal is then capable of predicting like the body pose, the entire body pose, despite that it's only being recorded on the foot plant. And But you need to have enough pixels. You need to have a lot of pixels on the contact ground in order to be able to predict the pose of the body. It's not very good with the arms, but it's pretty good predicting the pose of the legs and the torso, despite that they are quite far away. So I'll conclude here saying that one of the challenges is that these systems, in particular multimodal AI systems, require a lot of data in order to train. And this is very different from how humans learn. Like if you think of the amount of data that a human gets to see in the first 2 years of life, it's just that tiny, small sphere there in comparison with the amount of words that something like ChatGPT has seen since the beginning of its training. So with that, I'll end here. Thank you.